Before we begin, we'd like to say sorry for how long this video is. We'll make a series out of it. This simple mechanism can help us learn calculus and leads us to one of the most pure and elegant functions ever found in math, next on Quantumputing.
Okay, so what you just saw was this wheel moving outward, and if you could see it, it was getting faster and faster as it moved outward, in both distance from the center and in rotations. And if you're experienced with differential equations, you can try to solve for how much out it would be after a given amount of time. But first, let's take a look at the mechanics. So you can see we have a pulley here and two pulleys here. This pulley is connected directly to the omniwheel, so that means when the omniwheel spins, it also spins. As you can see, there are two strings that are wrapped around the pulley. When the pulley spins, it pulls these two strings inward as they wrap around the pulley. This causes, and you can see these strings are being redirected by these two pulleys and are fixed here. And you can see that these lengths here have to become shorter as this spins, since they're slowly getting spooled in. And so the wheel, as it spins, is essentially pulling itself outward. So you can see the more I spin it, it's just pulling itself outward because these string lengths are forced to get shorter. And so what basically ends up happening is, and since the wheel, as you can see, when it's farther out, it's going to spin faster than when it's really close in. So what ends up happening is kind of like a loop. First, the wheel starts spinning, which makes it go faster, which makes it go outward faster, which makes it go faster, which makes it go outward faster, etc. And so the result, when we find the actual equation, is really satisfying, and we'll get to that at the end of the video.
Also, you might be wondering, what kind of a wheel is this? Well, it's called an omniwheel. So it has these rollers that can spin independently of the actual wheel itself. So this wheel can go side to side without much friction. So it can slide along the shaft and get forced to spin by the disc, which is really helpful for us. Go ahead. We encourage you to try it out for yourself. But before that, let's try to solve a simpler example. So we have a problem for you. Let's say this wheel starts 1 inch away from the center, and its radius is 1 inch as well. So we're also going to spin this disc at 10 RPM. Now, while it's spinning, I'm going to move it 1 inch per second toward the other edge. And as you can see, it'll get faster as it goes further away from the disc. And so our question is, if we do it like this, starting 1 inch away and going 1 inch per second for 5 seconds, how many total rotations will the wheel spin?
But before we get right into solving the problem, it's calculus time. Okay, so let's look at the fundamental theorem of calculus. But before that, we must go over a few notations. When we write d over dx of some function f, we mean the derivative of that function. F dash for short. When we use this weird s symbol, that just means the integral of f of x. And we'll learn what an integral is after taking a quick refresher of what a derivative is. So let's say we have some function f of x. The derivative of f of x is going to be the slope of f of x at any point. So if we take some point on f of x, the slope of the tangent line is going to be the value at the corresponding point on f prime of x. And we'll get some quadratic equation, and the two zeros of that quadratic equation correspond to the flat points on f of x. So now let's look at what an integral is. One possible definition could be the area underneath a curve. And this just means the integral of f of x would be the area underneath it from 0 up until x. Another definition would be the opposite of a derivative. So that means the integral of the derivative of f of x is just f of x. So what does area have to do with slope? That's a very natural question. Well, we're going to assume that an integral is the opposite of derivative and show why it would be the area under a curve. Okay, so let's start with the graph of f prime of x. Suppose it's y equals x. Now let's try to find f of x, its integral. So let's take a step of 1 along f prime of x. The corresponding value will also be 1. If we take a step of 1 on f of x, the slope at that point needs to be the value on f prime of x, which is 1. So the slope needs to be 1, therefore the rise needs to be 1, since rise and run need to be equal when the slope is 1. And we can take another step of 1 on both graphs, and this time get that here the slope needs to be 2. The rise needs to be twice the run, so the rise needs to be 2. And we can take another step of 1, and this time get that the rise needs to be 3. So the total height of the graph after 3 steps of 1 is 6. 1 plus 2 plus 3. However, there is a slight issue. If we go in between 2 points, the value does not match the slope. This is because the step of 1 that we took was too big. So now let's do the same thing again, but this time instead of taking a big step of 1, we'll take a step of 0.5, and the corresponding height will be 0.5. So when we take a step of 0.5 on f of x, the height needs to be 0.25, since the slope is 0.5, so the rise needs to be half the run. We can continue doing this, each time taking a step of 0.5 on both graphs and figuring out what the rise needs to be. After a total of 6 steps of 0.5, the total height of the graph will be 5.25, the sum of all the previous rises. And you can think of this sum as the sum of all the previous slopes each times this step that we took, 0.5. And this is because the rise is the rise over run times the run, the slope times how much we went across in the x direction. However, we do have the same problem. If we go in between 2 points, the slope still does not match the value. So, let's do the same process, but now take a step of dx, and we'll get that the rise now needs to be dx squared, dx times the run, dx. And we'll get some curve. And the total height after n steps of dx will be the sum of all the previous rises, all the way until n dx squared. And you can think of this sum as the areas of these rectangles. The height of each rectangle is some number times dx, and the width is dx. And so we can sum all of these rectangles up until the rectangle whose height is n dx and whose width is dx. And if we call this sum s, you can see that as we take smaller and smaller dx's, this sum approaches the area under f of prime of x. You can see that here, it gets closer and closer to being the area of that triangle. And this doesn't just work for y equals x. We could have y equals x squared, for example, as our f prime of x graph. And we can do the exact same process and find that the slope needs to be dx squared. So the height needs to be a dx cubed, because it needs to be dx squared times the run. And so we can do the exact same process, continuing, taking a little step dx every time, seeing what the slope has to be, and finding out what the run is. And we'll get some curve. And once again, after some number of steps of dx, we will see that the height of the graph will be the sum of all the previous rises, which can once again be thought of as approximating the area underneath the curve.
Okay, I kind of understand, but what does dx do?
Well, the integral represents the sum of rectangles, and if you're familiar with sigma notation, this might be an easier way to look at it. So, suppose you have the integral of f of x dx, and I should mention that these bounds just represent the area from one point up until another point. And you can write this as the limit, as dx approaches 0, from n equals 1 to k over dx of f of n dx times dx. And this is up until k over dx, because k over dx is the number of dx's that fit in k. So that's the number of rectangles we'll be adding. And this whole limit thing, the integral is just a sleek way to write that, and whatever's inside is pretty much the same. Now let's look at a more visual way to understand the same concept. This time we will assume that an integral is the area underneath some curve and show why it would be the opposite of a derivative. So here you can see the purple graph is the integral, or area underneath g prime of x. And we will now increase both graphs by some tiny amount. Let's say it's delta x. What we want to know is, during this tiny change delta x, how much does the purple graph increase by? Well, it will increase by the amount that the area underneath g prime of x increased. And this is the area of this yellow sliver, which can be approximated as the area of the black rectangle. Now let's take a look at the slope of the purple graph at the point we stopped it at. This will be the slope of the yellow segment, its rise over its run. So this will be delta g over delta x. And delta g, as we just learned, represents the area of the black rectangle. And the tiny step we took, delta x, represents the width of the rectangle. So delta g over delta x, the area of the rectangle divided by its width, will be the height of the rectangle.
Wait, but the area of the black rectangle is just an approximation for the yellow sliver, right?
You're right. However, this approximation becomes better and better as delta x approaches 0. So in the limit, this height does in fact equal the derivative of g of x. So we have geometrically found why the height of g prime of x at any point is the derivative of g of x. Okay, now let's look at differential equations. At first this might sound a little bit intimidating, but they're really just like ordinary equations where you have to solve for some variable x. You do some operations and you get that x is some value. X represents 2 in this case. Differential equations are just like that, except instead of solving for a variable x, we solve for functions using operations like integrating and derivating. So here we integrate both sides to cancel out that derivating option, and we get that f of x equals x squared. Plus c though. There is this plus c, and this plus c represents that x squared can be shifted up or down by any amount because the derivative of a constant is just 0. It doesn't change the slope. We can also have some more complicated equations like this quadratic equation here, which can be pretty hard to solve if you don't know the quadratic formula. We can also have some very complicated differential equations, such as the second derivative of f of x is 2 times f of x squared. We can also have some systems of equations where we have 2 equations and 2 unknowns, and our goal is to find 2 variables. That also can happen in differential equations. We can have 2 functions f and g, and differential equations that relate them, and we have to find f and g. And these can be super, super hard, sometimes even impossible. Okay, so we learned what the fundamental theorem of calculus was. We looked at differential equations, and now we are finally ready to solve the problem. First, let's define some variables. Omega 1 will be the speed of the disk, omega 2 will be the speed of the wheel, whose radius will be r. D will be the distance from the center. D0 will be the distance from the center at the very beginning. R will be the total number of rotations of the wheel, and S will be the speed at which we're pushing the wheel outward.
Units?
Oh, I'm sorry. I'll let those in. And what we want to know is how much will the rotations of the wheel be at t plus dt seconds, based on what it was at t seconds. And we can use this equation to find out. R of t plus dt equals R of t plus omega 2 delta t. This omega 2 delta t term represents how much the wheel moves over delta t seconds. Omega 2, the speed of the wheel, times the time at that speed. So now let's find omega 2 in terms of the distance from the center. To do this, we will use this diagram. Suppose the wheel is a distance d away from the center. This point will have some velocity v. One way to express v would be the velocity of a point on the edge of our wheel, This will be omega 2 2 pi r. Another way to express v is the velocity of a point distance d away from the center on the disk. This will be omega 1 2 pi d. We can set these two quantities equal to each other and then solve for omega 2, and we will get that it will be equal to d omega 1 over r. D can be set to st plus d0, since s is the speed at which d is increasing, and d0 is what it started at. Now, let's draw a graph of r versus t. Suppose we want to take the derivative at t. We'll take a tiny step delta t, and we'll call the corresponding change in height delta r. The slope of this segment will be delta r over delta t. And so the derivative of r is going to be the limit of this fraction as delta t approaches 0, as this line segment becomes closer and closer to becoming straight. But what is delta r? Well, delta r is what the value of the graph is after the change in delta t minus what it was before it. So this will be r of t plus delta t minus r of t, and we can substitute in what we found for r of t plus delta t, and get that delta r is omega 2 times delta t. And when we evaluate the limit expression, the delta t's cancel, and we just get omega 2. So the derivative of r is just omega 2, which we found to be st plus d0 over r times omega 1. Now it's time to solve the differential equation we just found. So we have that the derivative of r is st plus d0 over r times omega 1. But how do we solve this? Well, we can start by integrating both sides. And as we learned earlier, due to the fundamental theorem of calculus, when we integrate the derivative of r, we just get r. And so therefore, r of t is going to be equal to the integral of st plus d0 over r times omega 1 times dt. We can factor out the omega 1 over r term like this, and then split up the integral into two separate integrals added together. Now, when we solve the first integral, we get omega 1 s over r times t squared over 2. This comes from the fact that we're finding the area of a triangle. The second integral is just the integral of a constant term, so that's just going to be a linear equation. So we can rewrite this in the form of a quadratic equation, like this. So we have something times t squared plus something times t. And we're just done. We found an equation. Or did we? There's this plus c term at the end. Remember when we talked about integrals? All integrals have a plus c term that can lift them because their derivative stays the same. So what is c? Well, to find c, we're going to see that r has to be 0 at the very beginning. And when we plug in t equals 0 to the equation we found, we get 0. And that means for this condition we just said to be satisfied, c must also be 0. And so c is 0. And this is how you find c. You always check what is going to be the starting value of this function. And now we are actually done. We have found our equation, and we can just substitute the values. And so we can just quickly plug this into a calculator, and we can see our nice quadratic curve, which is time versus rotations. And when we plug in 5, we get a final answer of 2 11/12.
You forgot something. Your units! You forgot your units on the final answer!
Oh, I'm so sorry. Sorry. That's in rotations per second. So after 5 seconds, the wheel will turn just under 3 rotations. Okay, so let's get back to the machine. Here, you can see we have a paper roller that will be spinning like this. There is also a marker pressing against it, like here. This marker moves with the wheel. So as the wheel moves outward, so does the marker. While the wheel moves outward, the paper will also be spinning. And so the marker will be drawing a graph of the wheel's distance from the center with respect to time. In this case, the wheel's distance from the center will be on the y-axis, which is the long side of the paper, and time on the x-axis will be the short side of the paper. So let's draw the x-axis. We'll uncap our marker, move it all the way to the end, and it will draw our x-axis, as you can see. This is also how it will draw the main graph. So this right here is our x-axis, and time is going this way. Now, let's draw our y-axis. Okay, now that we have our x and y axes, we can now start setting up our machine for working. Okay, now we can uncap the marker and move it over to the origin. We'll now put on this gear, which connects this shaft to the roller. And we are ready to start our machine. Okay, and we are done graphing. And let's take off the paper and see how it looks. And look at that beautiful graph. We have distance versus time.
But what could this graph be? To find out, we will derive the equations from this mechanism.
First, let's take a look at some variables. Omega 1 is the speed of the disk, r will be the radius of the wheel, d0 will be the distance from the center at the beginning, and p will be the pulley circumference. These variables are given by the parameters of the machine. Okay, so on the right you have omega 2, the speed of the wheel, d, the distance from the center, and r, the number of rotations of the wheel. These are variables that will just help us in solving the problem. So here we have two diagrams, two different views of the pulley system on the wheel. So we can see that as the wheel turns, the strings will be spooled in and pulled in. And somehow this is pulling the wheel outward. But why is this? Well, imagine you have a big block and you're on roller skates trying to pull a rope and pull that block toward you. Well, when you try to pull that rope, since the big block is so hard to move and you're on roller skates, you will end up pulling yourself and moving yourself rather than moving the block. The same thing is happening for the wheel. It's trying to pull the strings, but the strings are fixed at the end, so it's ending up pulling itself. And so every time the pulley turns once, the strings will get spooled in by the pulley's perimeter, P. So that means that the wheel's distance from the center will also increase by P. Okay, so what if the pulley turned more than just once? What if it turned n times? Well, then the string would get spooled in by n times P. And so it would move out by np. And so we have come across important fact number 1. This is that d, the distance from the center, is d0 plus np, where d0 is the starting distance from center at t equals 0, and np is the amount that the wheel moves outward every time the pulley turns n times. Now, let's see what the derivative of r is. To do this, we will see how the position of the wheel changes over some small time step, delta t. Let's suppose it changes by delta r. Delta r's unit will be number of rotations, so it'll be some fraction of a full rotation. The derivative of r is going to be how much the wheel moved over how much time it took for it to move that much. So the units of delta r over delta t will be number of rotations over seconds, which is rotations per second, which is omega 2, the speed of the wheel. So we have that dr over dt is omega 2, which we know we can write as d times omega 1 over r. We found this earlier in the video. We can think back to our important fact number 1 to replace d in this equation with np plus d0. So what is n? Well, n is the number of turns of the pulley, which equals the number of turns of the wheel, because they're connected. So we can replace n in this equation with r, and we can simplify a little bit and find out that the derivative of r is equal to some constant c1 times r plus some other constant c2. So we have come across important fact 2. This is that the derivative of r equals c1r plus c2. And for now, let's just assume these c1 and c2 don't make a difference, and the derivative of r is just r. What kind of a function would have a derivative of itself? So at any point, the slope, rise over run, would have to equal whatever the value is at that point. What would f be? Suppose you have $1, and every day it triples. So after 2 days, you have $9, and after 4 days, you have $81.
Wow, you'll have so much money.
Yep, you sure will. So this means that after X days, you would have 3 times 3 times 3, however many days it was going on for. So this would mean you would have 3 to the X dollars.
So much money.
Are you even listening? Anyway, now let's see how much money we gain from one day to the next. And what you might be able to see is that this gain in money is always twice whatever we had at the start of the day. For example, from day 3 to day 4, we gained $54, which is twice 27, what we had at the start of day 3. So the money that we gain from day X to day X plus 1 is twice whatever we had at the start of day X. And so every day, this should make sense because the money will triple. So it'll increase by 2 times whatever it started at. So this might lead you to think that the derivative of 3 to the x is 2 times itself. But this is not true. You're right that there is a constant there, but it is not 2. To actually find this constant, we would need to take smaller steps. We would need to see how much money we gain over a fraction of a day rather than a full day. And when we actually solve for this constant, we get about 1.08. So what if there was a base for which when you take that to the x, this constant turns out to be 1? Well, that number is e. When you take the derivative of e to the x and do the same process, this limit expression turns out to just be 1. And so the derivative of e to the x is itself. It's just e to the x. And this is what makes e so special. Now it's time to get back to our question. What was that mystery function that we needed to find? It needed to satisfy these 2 conditions. The first one being that its derivative needed to be proportional to itself plus some constant. This was important fact number 2. And the 2 constants we had found earlier. The second condition was that at 0, the function needed to be equal to 0 because the wheel hasn't rotated yet at the beginning. So we're going to start with a guess for f. We're going to guess that it's in the form of a e to the bx plus c and try to find a, b, and c that satisfy our 2 conditions. Okay, so we'll start by taking the derivative of our function. By the chain rule, we will get that this is b a e to the bx, which we can set this equal to c1 times our function plus c2. This is our first condition. We can now distribute the right side and see that BA e to the bx equals C1 A e to the bx plus C1c plus C2. And you'll notice that these terms match, meaning that their coefficients must also match. So B must equal C1. And we can now substitute that B equals C1 into this equation. And we get this new equation. Here you can see that these terms match, so the term at the end needs to be 0. And so we can solve for C, and we get that it'll equal negative C2 over C1. To find A, we will use our second condition, which is that at 0, our function must be 0. And we can substitute in values for C and B and get that A equals C2 over C1. So we've found A, B, and C, and we have come across important fact number 3. If some function f satisfies the two conditions that we had to satisfy, then f must equal C2 over C1 times e to the C1x minus C2 over C1. But we know what C1 and C2 are. So we can find r as a function of t. It will be d0 omega 1 over r over p omega 1 over r times e to the p omega 1 over rt minus d0 omega 1 over r over p omega 1 over r. Woo! That's a lot. Luckily, we can simplify some things down and simplify even more to get a final equation for r of d0 over p times e to the p omega 1 over rt minus 1. However, on our graph, we were plotting d, distance, as a function of time. And we can use important fact number 1 to relate d to r. And we can now write d as p times d0 over p times all that stuff. And we can simplify some things down and simplify some things down even further to get a quite nice equation for d, which is d0 times e to the p omega 1 over rt. We can just quickly check to make sure that this makes sense by plugging in 0 to this, and when we plug in 0, we do indeed get d0, which is good because we define d0 to be the starting distance from the center. And if we plot d of t on a function, it would look something like this. Now that we've finished deriving the equation for the wheel's distance from center versus time, let's compare it to what the machine actually drew. So here, we have a printed graph of the function we found. As you can see, we have distance on the y-axis and time on the x-axis. And the wheel travels just over 10 inches in about 6 seconds. And you might notice that this graph starts at 0 rather than at d0, and this is just because we shifted the graph down to match with the one that the machine drew on paper. Okay, so let's see how it matches. You can see here we have the graph that the machine drew, and we can now place the clear plastic paper over it and line up our axes. And we can see we have a pretty good match. Toward the end, it gets a little bit off, but for most of the graph, this is a very good match.
Thank you for watching our video for this long. We're sorry about how long it is, but we felt like we had a lot to say on these very interesting topics. This video was made for the Summer of Math Exposition 2, which is a friendly competition between content creators to teach math in a fun and engaging way. It's hosted by 3 Blue 1 Brown, a YouTube channel that teaches math in a fun and engaging way. We'd also like to thank 3 Blue 1 Brown for his series on calculus, which helped us a little bit in this video. If you want to learn more, check out his videos. If you wanted to know why we're doing this, it's not for that big grand prize you win if you win this competition. It's because we're just two 8th graders that wanted to make a YouTube channel to teach people how amazing math and science can be. If you like this video, feel free to do absolutely nothing at all. Or if you really, really want to, you can subscribe. Bye.